Hello everybody, welcome to this introductory lecture on Polymer Science and Processing. In this part of the lecture, we want to look into nonlinear step growth polymerization. So to recap what we did last week, we looked into a very rational approach on how to make polymers. This is known as step growth polymerization, and this essentially boils down to the following very simple equation. We employ organic chemistry. We choose monomers that have two A functional groups and monomers that have two B functional groups. And the only thing we require is that first the reaction works, and secondly, A only reacts with B. And if we do this in a very controlled way, then you see we get this reaction AA and BB, and from there on the reaction can go on more and more to form a long linear chain. So this is what we essentially discussed in quite some detail last week. We made a couple of examples, for example, polyesters, polyamides, polyurethanes, and then we looked into the theory on how to describe such a reaction. This is known as the Carothers theory, or based on Carothers equation. And what is essentially predicted is that in order to control such a reaction or to make polymers by such a reaction, we need to run it to very high conversions. So this is what you see here. Only if the conversion, so the extent of the reaction, approaches very high values, 99%, 99.9%, and so on, do we get large polymers. And this is a direct consequence of this step-by-step addition of monomers. Now you see, even if we link things, it takes a long time until these longer and longer chains actually connect and then form really long chains. And the second very important consideration we looked into was the effect of stoichiometry. And there we found that it's really essential that A and B are present in equal amounts in the reaction. If this is not the case, then we will never get large polymer chains. Now this of course seems like disadvantages, but we also discussed that the big advantage of this reaction type is that we have the functional groups straight in the backbone of the polymer. And this allows us to tailor the affinity of individual polymer chains, and that makes very high performing, durable materials. Okay, so what we want to do now is to look at what happens in a nonlinear step growth polymerization. So first I will discuss with you what that actually means, what I mean by nonlinear step growth polymerization, and then we want to look a little bit in synthetic approaches, how we can achieve this, why this is important, maybe where you have seen such materials. And then again, similar to the lecture before, we will look a little bit into the theory of gelation. So again, we will employ Carothers theory, and we'll try to see if we can predict how long we need to run a reaction to get a polymer gel material. And at the end, we will look into hyperbranched polymer, and this is something that we will get to towards the end of the lecture, and I will discuss this then a little bit more. Okay, first, let's consider what it means to make a nonlinear step growth polymerization, and we will see what comes out of this is a so-called polymer gel. So essentially, the whole question, what we want to discuss, boils down to the following discussion. We know that an AA monomer and an BB monomer forms a long linear chain. AA and a BB monomer, thank you, forms a long linear chain. So the question I'm asking you now is, what happens if instead of two Bs, let's say we have 4 functional groups B here? And now we can somewhat rationalize this. Let's just use 2 colors to make this a little bit easier. So in the beginning, nothing much is changing. I mean, maybe we can just go down here to have some more space. In the beginning, we connect an A with a B, and now we can connect another A, but we can also, of course, connect another A here and here. And here we will bind B's again, and you will see now, again, we can add a lot of A's at pretty much all positions or randomly. And then we will add B's again, and you see eventually these 2 groups come into close proximity, maybe here and maybe here. And if we continue to do this reaction, what will result is a very tightly linked network of polymers. So simplistically speaking, by this non-linear reaction, so it doesn't lead into a linear polymer chain. We will eventually connect all the monomers, or better connect of the polymers. So essentially, if the reaction is run to completion, what we have in our reaction mixture is one single huge molecule that contains all the monomers that we had in our solution. So we have only one molecule. If we define a molecule as a chemical species that is covalently bonded to other chemical species. And what this means is that we have a polymer network. So all the chains are interconnected. Or this is also called a thermoset. And thermoset simply implies that you heat up the reaction to actually perform the reaction, and then it sets in a certain arrangement and you can never remove it from this. And in contrast, a thermoplastic would be a material that you can heat up and then it melts again. This one here cannot melt anymore because melting implies multiple molecules start to move separately. If they're all connected, this cannot happen anymore. So this is known as a thermoset. So let's see what kind of consequences does this have. Maybe put this here. So we already said it cannot melt anymore because, as we said, melting implies molecules to move. Or, what we will discuss in much later lectures, technically speaking, melting only occurs for semi-crystalline polymers, but we can say it doesn't become liquid. So we cannot, for example, remold it. No, it will keep its shape. But also, if we only have one polymer or one molecule, we cannot dissolve it anymore. Because dissolution again means that individual molecules are separated from each other by a layer of solvent around it. And now, especially if you run the reaction in this way, that you have a lot of cross-linking points, a lot of network formation points with respect to this polymer A here, then we also do not have any chain mobility anymore. Because chain mobility implies that individual chains can move past each other and make the material dynamic. If everything is connected very kind of solidly, then there's no dynamics. Well, no is of course a strong word, but one could say limited chain mobility. So there again you see why this is interesting. Now, if the chains cannot move against each other, then of course it's a much harder and more durable material. So you can imagine if you try to pull this apart in a normal linear polymer material, you can eventually pull individual chains apart. Think about again the spaghetti. If you pull long enough or patiently enough, you will separate the piece of spaghetti. Now think that the spaghetti are interconnected everywhere. So you can pull as much as you want, you will never be able to separate the chains. In order to break this material, you need to break all these bonds that run through the material. And this requires a lot of energy, which makes it a very hard and tough and durable material. Okay, and the second thing, of course, is if it cannot dissolve, then it's chemically very resistant. Meaning it is not being attacked by chemicals, by solvents and so on, because it cannot dissolve. And this makes it very attractive for any application that requires something that should stay in place, that should stick, that should not break, and so on. And this is exactly what we use these materials for. Okay, so with this kind of short introduction, we can pretty much, so here you see this again, we will from this thermoset, we can directly go into the applications or into material classes where we apply this concept and especially this hard and durable nature. Maybe one additional point, what we discuss here in this context of thermosets and hard and durable materials is when we really have very close networking points. The situation is somewhat different if we have really long polymer chains A or very little amount of B. Then we have a very loose linked polymer network, and this we typically either call a polymer gel or an elastomer. But this is something I would like to discuss a little bit later in one of the following lectures, and here we'll mostly focus on examples where we have these tightly connected materials. Okay, so technologically or technically relevant examples. So we can start with polyurethane resins. If you remember from last week, from our discussion in last week, we already said that polyurethanes is really a very broad materials class that can be used for a lot of different things. Now, anything from a mattress to a very hard bicycle helmet or wood coatings and so on. And the possibility to tailor these properties arises from the use of different alcoholic units. And this can mean we can make either something very soft or we can make it very strong. And just to very quickly recap on how this worked. So polyurethane resins. Resins again implies they are cross-linked. What we need is the diisocyanate component. And when you remember our lecture from last week, and we discussed that we let this react with a diol and we form a linear polymer chain. So what you typically do to make a resin, you react this with something that contains more than 2 alcohol groups. And this is often molecules that look like this. So we have a CH2, a CH chain, so something like this. I mean, this could also be a higher functionalized species, doesn't really matter. But you see that this contains 2 information. A, we have more than 2 OH groups. Which implies that we will form a network eventually. And the second thing is that we have flexible spacers here. You see these contain smaller chain polymers as well. And depending on how long these chains are, we create more or less distance between the cross-linking points. So let's call this flexible spacers with controlled and this adjusts the flexibility of the material. The longer we make the chains, the less crossing it is, the more it can yield to external pressure, so the softer it becomes. The smaller the N here is, the less flexible it is, the harder the material becomes. And of course, if we want to make something really hard, we go away from such a material that has aliphatic chains and we replace it by something aromatic to make something really stiff and really hard. But this flexible spacers and with controlled chain length, we can use to adjust or control the mechanical properties. So the mechanical properties are pretty much always hidden in fine details of the molecular structure. This can make a difference from the stiff bicycle helmet to the soft princess on the P mattresses, okay, that we discussed in the very beginning. And again, of course, this is true for polyurethane resins. So this would be a material that you use to paint your garden furniture, for example, to make it very stiff. If we want to make a foam, as in the mattress or the helmet, we need to imply this possibility to generate CO2 if we add water. So if we add here plus H2O, so the OCN NCO will react to NH2, and this will produce the foam, so the whole thing foams up. If we work in a water-free environment, we don't get this, we don't get any foam, we get a continuous coating, for example. I'm not going to do the chemistry again, this is something we did last week, so we can pretty much leave it like this. Okay, so the next thing I want to discuss with you are silicone rubbers. And in order to do this, I first clean up the blackboard. So silicone rubbers, they are generally very hydrophobic. They have this possibility or this characteristic that it tends to de-wet a lot of liquids. So the surface energy is very low, and that means materials do not stick on them very easily. It's a very flexible material, and I'll come to this in a second, and it's also biocompatible. And this makes it a very special material that finds very important applications. So now if you think for yourself, where do you know or in which applications have you seen or come across silicone rubbers? Well, one thing that I guess by now pretty much all of you will have in your kitchen are some silicone-based kitchen equipment. So you see here these beautiful crocodiles that you can use to take stuff out of the oven, but you also know these as kind of forms and materials to bake a cake with. That makes it very easy to remove the cake, for example, like muffin forms and cake forms and so on. So why is that? It's very flexible, so that makes it easy to remove things. It's also very temperature resistant. You cannot use a lot of polymers to touch a very hot oven, and in this case it's not a problem. And it doesn't allow sticking too well, so it also makes it very easy to remove things. This is what makes it very attractive for kitchen applications. Very similarly, you know this probably from your bathroom as insulation. Now, if you check next to your toilet, next to your hand wash basin, next to your bathtub, then you will see that typically the walls are insulated by the silicone paste. And here, of course, the possibility to repel water very efficiently. So this hydrophobic character is very important. Well, then we know it from prosthetics, implants, and so on. So anywhere where you want to have soft materials, for example, here in earplugs, know that you want to be nice and soft to not damage your ear. This is also a very important property because it remains flexible and it's biocompatible. So you can put it in your ear without getting problems. And you find this quite a lot in medical tubing because it's flexible, so you can bend it around, and it's very inert, so things do not stick on it. And again, it's biocompatible. So as you see, it's really a material that is used for a lot of different things. And now let's see why, first of all, how we can make this and why and how these special properties arise. Silicone rubbers. So as the name already implies, silicone-based materials are based on silicon. So the element silicon. And now you can buy these or you can synthesize these to contain different functional groups. So it can either contain some organic inert components, which are simply called R for rest here. And this is, for example, a CH3 group or a longer alkyl chain or whatever, anything else. And it can also contain chlorine groups. And these chlorine groups, when they come in contact with traces of water, they will first hydrolyze. And why that is because water, again, is nucleophilic. So the high electron density of the oxygen can make a nucleophilic attack on the silicon because this will be partially positive as a result of this highly electronegative chlorine as a neighbor. And then it will kick out the chlorine and you will get this type of material. And this type of material can now further react with other materials to form RSI to form such a silicone bond. Okay, this alone doesn't make a polymer, and we'll get to the polymerization in a second. But the general reaction is a polycondensation reaction because water is released here. And again, why this happens is because now one of these OH groups will attack the positive center of the silicon, and then water will be replaced, and you end up having this type of bond. Okay, so now, maybe if you want, I can also show it to you. But I think this is fine. Okay, so now how do we make polymers from this? We have now a molecule here that only contains one functional group. Let's put it here again. Now we can also have materials or molecules that have two functional groups. And then similarly we can have three functional groups, and finally four functional groups. This is all things we can buy. Now we can see how they relate to a polymer formation. Now very similar to what we discussed before, this could be considered an AA monomer because it can react here and it can react here. and this material will form a linear polymer. So this will form a polymer. It looks like this. Now this has 3 functional groups. And as we discussed before, anything with more than 2 functional groups will form networks. And by the way, if we only use this one here, we simply end up with inorganic glass. Right? There's no organic group anymore. This will become SiO2 as a 3-dimensional network. This one here still contains 1 functional group and can form an organic network. And this one here will terminate the chain. Simply, if you want, it acts as a stopper. No, once this has reacted, nothing can continue to grow anymore. So you see now we have a toolbox that we can use to change or modify or control the properties of our polymeric material. If we only use this one, we get long polymer chains. If we mix in this one, our polymer chains will become shorter. So the material is likely not to become solid, but maybe a viscous liquid. If we start to add these ones here, then our linear polymer chains will start to be converted into a polymer network, so it will become stiffer and will become more resistant. And also it will form a beautiful rubber, but this is something that we will discuss in one of the later lectures. And the more of this we add, or even this one, the stiffer our polymer becomes, or our polymeric material becomes, and the less flexibility we have. So that means by adjusting these components, we can really control the mechanical properties to make something very flexible, to make something a little bit harder, up to a material that is relatively stiff in itself. And this is, of course, very useful if you want to adjust it. For example, in prosthetics, you may want to have it a little bit harder. In some other cases, you might want to have it very soft so that it conforms well to the ear, for example. If you do your bathroom formation, you want to have it a little bit stiffer in order to avoid that it's easily getting mechanically damaged, and so on and so forth. So this is really the special properties of the silicone material, that you can control it very well, and that it has these very interesting properties by itself. By itself, this chain is very flexible because we have an SiO bond that can rotate very easily, and this makes it very flexible. Okay, so this is how we do silicone rubbers. Now let's move on. So again, here you see, this is maybe one of the most famous materials, is PDMS, polydimethylsiloxane, and this is something that you can buy. Okay, and you see there's a lot of different applications that we can use this for. All right, so the next material that you probably know are known as epoxy resins. So again, I invite you to take a second and think about where you may have heard this before somehow in your daily life. Possibly not really as the name epoxy resin, but this comes in kind of a very well-known product, and this is 2-component glues. So if you go to your hardware store or something is broken in your house and you want to fix it, you go to a hardware store and tell them, I need a very potent glue that can fix my favorite plate, my favorite toy, my bicycle, whatever this may be, that can fix this together. Very likely, the salesman, at least if he or she knows what he or she is doing, will recommend a 2-component glue. So this is a very important category of glues, and this is how they look like. So you have these 2 tubes here. One is known as the resin, and the other one is known as the hardener. No, and you can store these 2 for a long time. Once you mix them together and you kind of stir it a little bit, it starts to harden relatively quickly. In this case, you see it takes 2 minutes for it to form a very, very solid material. Depends a little bit on the glue or on the receptor. You can also buy some that take longer, depending on what you want to do. And now what we want to figure out is how this chemistry works. So essentially, what is in the two tubes and why can you store it independently and why does it react when you mix it together. Just as one application, you see, if you know these really, really big wind generating turbines, these wings here are often made by composite materials of glass fibers that are fixed together with epoxy rubber. Same goes for insulation in big turbines and so on. So you see it's a really sturdy, mechanically stable, mechanically robust material. Okay, so what is the chemistry behind Epoxy Clues? And also there, I want to go to the blackboard and discuss this a little bit with you. So we already know there's two tubes. Let's first look what is in the first tube. Tube A, and this is the that actually contains the epoxy component. So first, maybe to clarify, does anybody know what an epoxy functionality is? In organic chemistry, you think back to your organic chemistry lecture. Epoxies look like this. So it's a three-membered ring containing two C atoms and one oxygen. And even without deep knowledge of organic chemistry, we can already somewhat anticipate that this is not the most stable molecule. Now what we know is that normally C bonds tend to have a tetrahedral angle and they like to form 5 or 6 membered rings. Now, so if it expands in this way, then it can form this without any strain. If we now force these bonds together very tightly, there is a natural tendency, or there's a natural strain in this ring, and a tendency to open up, to release this ring stress is very pronounced. And secondly, we have an electronegative component directly next to an electropositive component. So naturally, these materials are very susceptible to be attacked here by something that contains a lot of electrons, so a nucleophile. Because then the ring can open up, you release this ring tension, and this C atom can get more electrons. Okay, so this is kind of the idea behind this chemistry. But let's see, first of all, we need to make these epoxies, and we need to make them in a way that we can, at the end of the day, fill them into a tube and sell them as a glue. And how this is done is using these two molecules here. This is known as epichlorhydrin. So it's a material that you can buy, fairly toxic material, fairly reactive material. And you let this react with a dialcohol component. So very often you use this bisphenol A component, simply because it's a very stiff material. And to make our life a little bit easier, I will abbreviate this with stuff like this. Okay, so we don't bother with the inner component, that's just some organic material that doesn't participate in the reaction. So now we do this under a basic catalyst, and what a basic catalyst does is it deprotonates the alcohol. So this makes it much more reactive. Okay, and now this deprotonated alcohol, which contains a lot of electrons, is of course very potent in attacking this material here. So what it will do is, as we already discussed, it will attack this carbon atom here, opening up this ring. So in the first step, what we will have is start here with the C atom. And maybe to make it a bit easier, let me just write it down. Well, sorry, we start here. So we have the Cl. This is the C atom. Then we reach this C atom here. And this contains this negatively charged oxygen because this bond has been broken. And then we reach this C atom here. So this now has a H2 and an alcohol here. And this can, of course, happen on the other side as well. So then we have the same thing, CH2, CHO minus CH2, Cl. So I made the reaction twice on both of these sides. Kind of like this. Okay, so now we have this negatively charged oxygen species on both sides close to this structure here. And we know that a chlorine atom is a fairly good leaving group, so we can kick this out as an Cl minus ion. And keep in mind, if we have a base here, this was typically let's say, NaOH, no, an inorganic base or so. And this means that we can form NaCl or so. Okay, so what happens is that these electrons attack here, kick out the chlorine, and actually an epoxide is recovered. So we apply some temperature to actually force this reaction, and we remove NaCl from this base here. And then what we end up with is a material that looks like this. This would be the epoxide ring. We have our CH2 group here. We have an O, R, O, this CH2 group, this CH group, and the oxygen. So we now have recovered a longer epoxide that contains this material here. And then this reaction can go on a little bit more, because of course now this can attack here again, and so it starts to polymerize. And of course we could make a very long polymer here, but this is actually not our intention, because we want to have something that we can still fill into a tube and that we can also squeeze out of a tube. So we need to suppress the reaction at early stages, because we want to keep it in a liquid state. So how we do this is by adding, where do I put this? Maybe here. Polymerization not wanted, because it needs to come out of the tube. And now we employ what we learned from Cavotha's theory. We know that in order to make a good polymer, we need to take these two in stoichiometric components. So if we add an excess of this epoxide, then it will not run into a large polymer, but it will keep as very short oligomeric chains containing only a few units. So we form only short polymers, and equally important, these short polymers will have this epoxide function as end group. So the polymer is, if you want, we force it to terminate in the way that it has an epoxide at the outside. This is in the first tube. Something that looks like this, and possibly a little bit longer in the middle here. Okay, so now the question is, what goes on in the second tube? This is known as the hardener. And this tube contains this tube contains molecules that have multiple amine functionalities. And why that is, you can picture here. So one amine can react with an epoxide, very similar to what we just seen with the OH group. Now again, what we discussed last week, what is true for alcohols is mostly even more true for amines because they're even more nucleophilic. So this electron lone pair can also attack here. This will open this bond. Let's make some more space. This attacks here, so we have a CH2. When this attacks, this opens up. Now, since this lost its electron pair, it has a positive charge. This has a negative charge, so this can easily equilibrate by taking over a proton from the amine, and at the end of the day we reach we connected the amine to the epoxy group. Now of course this is not where the reaction ends, and for this let me just make some more space. We've seen that one amine reacts with the epoxy and it loses one hydrogen. So if I now take a molecule that contains multiple amines, then this can react with one epoxide by binding, and how do I draw this most efficiently? So if it does this, so here it will then lose one proton and be connected by one epoxide. There's still one proton left, so this can react with a second epoxy polymer. And then it will form a second polymer, and the same thing is true on this side. So again it can react with one here and with one here. And if it does so, then again it will connect like this. So at the end of the day, you see that one diamine can connect 4 of these prepolymers. And if this goes on and on and on, of course you will connect more and more chains, and this hardens the material very efficiently. And now we can also directly see why some of these polymer or these epoxy glues harden very fast, let's say in 2 minutes, and others harden slower, let's say in 1 hour. This simply depends on what kind of amine you use, so how many amine functionalities you provide for this reaction to occur. The more amines you have in your molecule, the faster you form a networking point, and the faster the material or the epoxy glue solidifies. Now this is how we can tune the kinetics of this glue simply via the molecular structure. Okay, let's digest this a bit, and I clean up the blackboard once again. So now again, here's the chemistry of the epoxy. We see this pre-polymer that contains the epoxy groups, and here you also see it in its full length, what I simply abbreviated with R. You see here the second type of reaction where now the bisphenol A attacks one of the formed chains, and then you get these OH groups. And at the end of the day, you give an excess of these epoxy functionalities, and that leads to the polymer to be functionalized with epoxy groups at the outside. And then they simply cross-link. So again, you see this here. We have a diamine. This can connect to, each amine can connect to two polymer chains. So you very efficiently cross-link. And here you see what I said before. Depending on what kind of amine functionality you use, you can either have 5 functional groups, 4, 6, or 4. And this controls the speed of the reaction. So now, here's one last example that I want to briefly discuss with you, and that is bakelite. So as I showed you in the very first introductory lecture of this course, bakelite was one of the first commercialized polymers. And this is something that you still see nowadays, maybe less frequently than earlier, but you see this, for example, in very old telephones, in very old kind of switches and relays, if you go to the basement of your grandmother or so, or in these old radios. So these typical kind of old-fashioned, darkish, black, brownish-looking material. This is a bakelite. And what a bakelite is the condensation product of phenol and formaldehyde. And this, if it reacts long enough, forms these very complex polymer networks, and you see it contains a lot of aromatic units that are bridged that makes it very hard and robust as well. And I do not want to dwell too much on this, but I'm just going to give you the gist on how this reaction is working, because this may be a little bit less intuitive how this condensation works, maybe compared to other type of chemistries. Okay, so this bakelite, I think this is the T. This is a condensation product of phenol and formaldehyde, OH. This is a phenol, and this is formaldehyde. And now we first need to find the reactive centers here. Take a look for yourself and decide whether you can identify points in these molecules that may be reactive. So here this should be clear to everyone by now. This is reactive to something nucleophilic because it lacks electrons. Now again, the carbonyl group, the oxygen, here pulls the electrons away from the carbon and makes it susceptible to a nucleophilic attack. So now we are looking for something that can provide electrons. And since we already see that the reaction works, this must be somewhat related to this material. So somewhere here we must have or nucleophilic groups, so regions with a high electron density. And now there's a concept in chemistry that is known as Mesomeric Formulas. So this kind of is an estimation on where we have high and low electron distribution. Let me run you through this. Here are 3 electron pairs of the oxygen. And of course, this is all shared by the molecule. So there's these structure formulas just give an impression or very approximation of the electron density distribution in the material. And now if I flip around these bonds a little bit, we can try to see if we identify regions that have higher electron densities as others. So we can have one of these bonds flip in here, then we need to make space. So this can be just residing at this carbon atom. Sorry. And then of course, this negative charge can be delocalized in this aromatic system. So this can flip over here and the charge can move to the power position. And the same thing can happen in the other direction. So it can move here and then we have our negative charge here. So this doesn't mean that this carbon is necessarily negatively charged. It just means that the electrons can shift around in the system in these mesomeric structures and have higher electron density here, here, or here. But note, never here or here. Okay, so we have ortho or power positions that have high electron density. Nevertheless, we can use this to make our reaction. So this can be, for example, acid catalyzed. So and now we have our phenol here, and we keep in mind that we already know where our electrons can be. And if we add acid, then we further activate our formaldehyde. So via an OH bond, these electrons are being even further drawn in this direction, H+. So that means this is even more electron deficient. And that means we can use the high electron density regions of the aromatic system to attack this material. So now, while we do this of course will flip out and it can bind to the H here. So then we have a C here. This still contains 2 carbons, these are these 2, and we have an OH group here. And now the positive charge is in the aromatic system. Of course, this is not stable. An aromatic system always wants to regenerate its electrons. So it can do so by regaining this bond here. And this H can be taken over by the OH group. Now our aromatic system is complete again. We have here a CH2 and an OH2. And since this is acid catalyzed, well, I can simply go away here. and we are left with a positive charge on this C. And now again, now we have a positive charge. We still know that these aromatic rings have negative or have regions of higher electron density. So now again, let's put it maybe here. This can attack and then form an adduct. It now has electron deficient here, the positive charge now. And here we have a CH2. And here the entire aromatic system that was over there. And now, as I just wanted to say in the beginning, this whole thing is acid catalyzed, so we can simply kick out the proton here, recover our aromatic ring, and then have merged these two together. And this can now go on and on and on because we still have reactive positions here and here and let's see here and here, and all of these can condense further and further, and this is then how we can form a network. So typically use then accelerators to make sure that the network forms more efficiently, but this is kind of the gist about this reaction. So you see it involves a little bit more advanced chemistry, but nevertheless it's the type of polycondensation that leads ultimately to a very dense network of functional groups. Okay, with this I want to leave the part of chemistry, clean up some more, we can relax, and then we will discuss a little bit the theoretical aspects of our reactions. So again, you see this one, and now we want to go into the theory of gelation as predicted by Carruthers again. And in order to do this, let's just go to the blackboard once again. We look at the theory of gelation and we employ Carruthers equation, or Carruthers. Let's call it Carruthers theory. Let us briefly recapitulate which assumption we made before when we calculated the dependence of the degree of polymerization on the conversion of the reaction. So we had we postulated that we can calculate the degree of polymerization using N0 over Nt. And furthermore, so N0 is the number of molecules at T equals 0, and Nt are the molecules at a certain time t, so after the reaction started. And then we also had P, the conversion, of monomers, and we said that P are all the groups that have reacted divided by initial groups. Okay, and this we can express via the molecules that are involved. So we can say the reacted groups are the initial molecules minus the molecules that are still there at a certain time t. Now the difference gives the molecules that have reacted. And since each reacted molecule contains two functional groups, or maybe to be more precise, because this is actually not true what I just said, for what we want to do now, each reaction involves the conversion of two functional groups, an A and an B group. So this is why if we want to convert or express the reacted groups via the monomers, we need to add this factor of 2 here. And then this, of course, the number of initial groups, this is something that we need to figure out now. Let's remove this again here and then express this separately. So what we're looking for is, how did I call this here? NR, number of reacted groups at a time t, and this is the initial groups. So NR, if this is reacted molecules, then we need to add this factor of 2 to come to the functional groups. Now we have it. So the problem now is that before we could also always express the initial numbers of groups simply via NA and NB, so the numbers of functional groups. But since now we have more functional groups than molecules, this doesn't work so easily anymore. So let's first look at the reaction here. So our reaction that we assume is we take AA molecules and now we let them react with 2 B3 molecules. And the assumption I'm doing here, just to make our life easier, is that we have a stoichiometry. And now we want to calculate these different numbers. So the first thing we want to find is this number of functional groups. Maybe we can, and our problem is that NA or NB, the number of functional groups, do not relate directly to N0, because here we have more than 2 functional groups. So what we do is we define the average number of functional groups. So what we do is we count the groups and the molecules and then divide the groups by the molecules, and then we get a value for this. So this is F average, and it would be numbers of molecules with a certain number of functional groups. I divided by all the molecules. So this reads much more complicated than it actually is. So in our example here, we have 3 molecules with 2 functional groups. So this makes it 3 times 2 is 6. And then we have 2 molecules with 3 functional groups. So again, 6 functional groups. So this would in total be 6 functionalities. And we divide by 3 and 2 molecules by 5. So in our example, it would be 2 times 3 plus 3 times 2 divided by 5, and this equals 2.4. So 12 divided by 5. And if we do this, we can now express this initial number of functional groups, NAB, by the initial numbers of monomers. And the way we do this is simply NAB at time 0 is N0 times F average. So this is the relation that we need because we need this NA of 0 and we want to express it in the way of NA0 because eventually this will come into this equation here. Just for the check, in our case, N0 would be 5, 3 plus 2, and F average is 2.4, and 5 times 2.4 is 12. And that's exactly the number of functional groups we have in this molecule. So this relation holds, and now we can work with this to make the calculation. So again, now we need to go back to P. P, we have now found NAB of 0, and I already told you how to get this NR of T. So NAB of 0 is N0 times F average, and the number of reacted molecules times T is N0 minus NT. Okay, so these are the reacted versions. And now, in order to calculate the conversion, we take the reacted groups. So this one, N0 minus NT times 2, again, because 2 functional groups react to form one new polymer unit, or one additional unit in the polymer, and divided by the numbers of functional groups at the beginning, and this is N0 times F average. Okay, and now we can play around with this equation a little bit more. So first we can take out 2 divided by F average, and then we see what we have here is N0 divided by N0 is 1 minus NT over N0. And now you see this whole point of this endless transformation of units, because now we have something that we can relate to the degree of polymerization. Again, you see here, Xn is defined as N0 over Nt. So Nt over N0 would be 1 over Xn. So P equals 2 average functionality 1 minus 1 over Xn. And now typically we want an expression for the degree of polymerization as a function of the conversion and not vice versa. So we simply play around with this equation a little bit. Now separate this, get this on the other side, then invert the equation, and what comes out is if we solve for Xn, then we find that this is 2 minus 2 minus P F average. So now we found an expression that relates the degree of polymerization again to the conversion, but also to the average functionality. Okay, so far so good. This is what we also used in the beginning to find Cavotha's equation. Now we can first of all do again a sanity check, and we think about what happens if we convert this to a normal linear system. In the linear system we have AA plus BB, so the average functionality is 2. Now each molecule has 2 functionalities. So this would recover 2 minus 2 divided by 2 minus 2p, or 1 divided by 1 minus p, which is the normal Cavotha's equation. So if we don't have any additional networking points, we just generate our normal Cavotha's equation. Okay, but now we're interested in when do we form a network? So at which conversion will the network be formed? And now what we assume is a very simple thought that actually overestimates it a little bit, but we said in the beginning that a network means that all chains are connected. And if all chains are connected, that means that the molecular weight or the chain length becomes infinite, because suddenly everything is connected to each other and we only have one single large molecule. So the conversion for which this happens, so we call this critical, the critical conversion. P critical. And this happens when xn goes to infinity. And we see this goes to infinity if this becomes 0, and that means if P critical is equals 2 over F average. Because in this case, then the denominator becomes 0, xn goes to infinity, and now this is our criterion. This is how long we need to wait to form the reaction. And now we see we can now test different scenarios. In our case, this is 2.4. So in example, P equals 2 over 2.4. If we increase F average, so if we make more functional groups, then this becomes higher, so P critical goes down. And there again you see that you can change the kinetics of the reaction or how long you need to conduct the reaction by the choice of monomers. So in this reaction, quite naturally, the more cross-linking points you have here, the easier it is for the material to form a network. And this is given by this P critical. Okay? Good. So now we have an expression to know at which point of the reaction we actually, if we want to destroy our normal polymerization conditions and we form a complete network. And this is predicted by the simple Cavotha's equation. So we looked at this. This is what we see here. This is what we had here now. And here, for example, you see this, this overview. So here is F average. And depending on which conversion you have, you can calculate an xn. And you see eventually it becomes gelled. And you see it becomes gelled at lower conversions, the higher F average gets. So here you need to go to very high conversions to get a polymer gel, here much earlier. And of course the higher F gets, the more it will shift in this direction. Okay, just there's one problem. The theory is very simple, but it actually overestimates the critical conversion. So if you measure this, here's very old data from Paul Flory, you see that actually he defines that a conversion or the gelation set in when the viscosity goes to infinity, because suddenly the material solidifies, and the solid material, of course, has an extremely high viscosity. And you see this viscosity ramps up, and the average degree of polymerization when this happens has not really reached infinite values, but something more like, whatever, 20 or 30 or so. And the problem here is that we underestimate or we overestimate this critical conversion because our assumption is not entirely correct. Xn doesn't really need to be infinite. This is the result of the complete network, but it starts forming a network when we have some very long chains already that can connect to shorter chains. This is kind of the onset when the whole system kind of fails and then goes into this gel phase. And since there is already a few small polymers in here, or small monomers in here that are not connected, the average degree of polymerization actually has not reached infinity yet. But again, this is more a minor detail that shouldn't really bother us. The theory is very simple, and it just shows us that we can predict this via kind of very simple assumptions on the monomer conversion. Okay, finally, just want to show you one example how we can suppress gelation, and that is in hyperbranched polymers. So this is a hyperbranched polymer. We have one monomer A and one monomer that contains one A group and two B groups. And now my question for you is, will this form a gel or not? Think about this. I just clean the blackboard once again. And you can already think about it and maybe rationalize your assumption. Okay, so A and two B's. What will happen? And you may already guess, probably something special or something not intuitive. Otherwise, I wouldn't have or I wouldn't need to mention it directly. So we would assume it will probably not gel. Otherwise, it would fit well within the topic of the lecture. But now the question is, why doesn't it gel? Now see how the reaction proceeds. So A reacts with B. Maybe here as well. But let's just focus on this one here. On the first set of reactions, we already created 4 B's out of 2 B's. If we continue this reaction, this can of course react with an A again. And you see that with each reaction, we increase the number of B groups because there's never enough A groups to saturate this thing. So if you want, this is a molecular analogous to a Ponzi scheme. Now it always diversifies more and more, but there will never be enough A groups to actually connect back to any of the other chains because everything is always saturated by B's. And this is why you cannot form a network, but you will infinitely go on and on and on and form more and more B's. And this is why such polymers are known as hyperbranched polymers. They are by far no linear polymers. No, they are much branched, but there are also no polymer networks. And let's use the last 5 minutes of this lecture here to see why this is interesting. So here again you see this. Gelation is suppressed because we have so much B with respect to A. And why are hyperbranched polymers interesting? First of all, they have special properties. Their viscosity is lower compared to linear chains. And why that is fairly clear. Linear chains can very easily entangle. These are much more heavy things that are not so easy to get stuck in each other. They're very amorphous materials, simply because they have so many branching points, which can be good for transparency or to tailor material properties. They have a very good solubility because they cannot pack so easily because of their branched nature. And of course, they have a very high density of functional groups. So if you go back and now think about maybe the functional group B could be an amine. Amines are very good at binding metal ions, for example. And if you start the synthesis, you create a huge Christmas tree full of amine functionalities, or full of whatever functionalities be. And if you find an application that requires B functionalities, then you're in business here. Then you have a lot of these available to do whatever you want to do with them. So why is that good? For example, in filtration or purification, because you can take these to filter out, for example, toxic ions from drinking water. They could be good for some type of electronic materials because they can be easily processed, because of their lower viscosity. So you can make very good coatings with them, or you can make electrolyte membranes. They are amorphous, so everything is kind of penetrable, and they have this very high functional group density. So they can act as very good polyelectrolytes. Okay, with this, I'm at the end of today's lecture. And let me briefly summarize what we learned. First of all, we call a network a polymeric material where the polymer chains are connected together. And as a consequence, the material becomes insoluble, non-meltable, and we typically call this a thermoset. We also saw that we can tailor the properties by changing the density of the functional groups. We also saw that these networks can form through nonlinear polycondensations. That's not the only possibility. I will show this to you in one of the upcoming lectures. And we see this can be interesting commercially, not only in earlier polymer times, but whenever you require something hard and durable. Now, think about the epoxy glue. Then we looked into the theory of gelation, and we saw that we can connect this network formation with a critical degree of conversion, so that for some time it starts to branch, and eventually it kind of backbites and then connects all the chains. And we see that we can avoid this network formation if we choose the proper molecule, which are these AB2 monomers. And with this, I'm at the end of my lecture. I thank you very much for your attention and looking forward to seeing you next week. Goodbye.